So let us welcome our fourth speaker in the series, Introduction to Science Education, Kamal Mahendroo, who works at the Vidya Bhavan Educational Research Center in Udaipur. Kamal has been in the field of science education since 1972, which is when he first stepped out of college university sphere into the world of science education at the school level. He went to the Hoshangabad science teaching program where he spent many years, and then later moved on to Udaipur VBERC, constantly engaging with teachers, students, people in textbook bureaus, in the state and NCERT teams, in not just creating textbooks but also in training teachers and engaging very closely with school children at all levels. He has a great, a very warm way of doing these things, which you will probably see in the next hour or so. And he also has a theoretical inclination, in the sense that he also likes to look at the formal aspects of science education, not just directly engaging with people in the field, but also thinking about these things, thinking about the theories of science education and so on. Kamal and I have a fairly long association, close to 20 years, and it's been a very enjoyable association. We wrote some things together, we discussed and debated a lot of things. We probably didn't fight, but we came close to fighting. But it's been an enjoyable journey all through, and I'm very happy that he's here with us today. He's going to talk to us today about a very dear topic to him, and this discussion, or this kind of discussion with him, always ends up running out of time. But it's always very, very enjoyable. I'm sure I'll learn a lot today, and I am quite sure you too will. So Kamal, over to you, and the time is now yours.
Sure. Thank you, Bhas. This is my fourth visit to the ISER campus here, and each visit unfolds new ideas and new levels of thinking, and this time in particular I've been able to interact with students also substantially, and I'm very thankful to the entire team for making this opportunity possible, with this added burden of speaking today evening, which of course causes a lot of tension. But I hope I am able to say something meaningful before all of you, and then hear your reactions. As I discussed with Bhas earlier, I am attempting firstly to share with you a broad theoretical framework that I have been struggling with myself to articulate, particularly because I feel we need to articulate these ideas at level of school teachers to be able to communicate with them, and construct a discourse at that level that appeals to science teachers, that communicates to them, and that in itself I think is a serious challenge for people interested in science education, both at policy level and at program development level. And secondly, I also want to ground my ideas and experiences in some concrete framework. So, I have just taken up a topic which I have enjoyed building up over the years, because I somehow realized that it was a topic which for many years from my school days we took for granted. ये तो समझ में आता ही है, कोई खास दिक्कत नहीं है इसमें, why seasons change and what is our solar system like, etc. And it was only when teachers in a workshop asked me, can you explain to us why seasons change, that I found myself in very deep waters. And from that day onwards I was trying to unravel how exactly our textbooks explain such a simple question, and the type of problems that textbooks and we teachers run into. And then also the potential of exploring such a question in a much larger framework of method of science and history of science. I hope I am able to convey to you some of the excitement that I have felt, that starting from such a simple question, one really reaches very deep questions of development of science and its methodology, which is at the heart of every good science teacher, that I must be able to convey this to my students. So, I think I will very hurriedly through a number of slides rush you through what I believe is a theoretical framework. I will not digress much on that, and maybe just expect you to read the slides with me hurriedly, just to get a idea of where exactly I am coming from, and then like to spend more time on the nitty-gritties. So, what should a good science teacher aim for in the science class? Traditionally we have accepted that science is an important body of knowledge, and that body of knowledge should be transferred to our students as it is, as we have it now. The latest we should be able to convey to our teachers, and all sincere teachers want to not just transfer it in the empty vessel mode, that the student is an empty vessel and let me fill it with knowledge. That is a very old metaphor which I think all of us react very strongly to, rightly so. But yet every teacher desires that I should be able to do it with some understanding. And also create some excitement, some curiosity in my students' mind. Of course, the system expects you to just convey that body of knowledge, lot of information, concepts, definitions. We just avoided getting into a very heavy debate about role of definitions in science teaching yesterday, though the question was posed quite starkly, and then I mean that is still largely the accepted goal, and as you go into higher classes it becomes more and more so that a good science teacher is who can give a hour-long lecture non-stop and yet make sense to the students and not get them to sleep, right. But again, I think if you look at all the discourse around science education, the expectations are far beyond that, and I will just try and summarize them in these slides. So, broadly we want to develop scientific knowledge in students, not just transfer, which means a knowledge with understanding, coming to terms with it, to be able to use it in future, and in terms of what exactly that knowledge comprises. There is a lot of informational knowledge, and I believe a lot of it is important also. I mean, without understanding that there is oxygen, there is nitrogen, and we can't really begin to talk about the environment and photosynthesis and so many other concepts. So, a lot of informational knowledge is needed, but that informational knowledge must connect to a lot of conceptual knowledge, concepts, but the concepts themselves build up into theories, theories leading to models, mental models of what we believe is the phenomena or nature, and mathematical formulations of the same, and lot of phenomenological knowledge, how the phenomena takes place in terms of the conceptual frameworks that we have formed, can we predict the phenomena confidently, how are we able to deconstruct the phenomena, etc. So, a lot of phenomenological knowledge is part of that. But any good science teacher is also equally concerned about developing skills and aptitudes around what we call the method of science. So, I think experimental skills top the list, experimental skills and which include measurement, estimation, designing experiments, analytical skills where we expect students to be able to handle different varieties and lots of data, graphical analysis, etc. A lot of those type of skills, ability to logically analyze, develop a rational argumentation, etc. Articulation, presentation and comprehension skills to be able to state what their understanding is, to comprehend what the others say within the framework of what we call the so called language of science, which has mathematics also in it, but apart from that it has its own specific meter and more. I do not claim this to be an exhaustive list, but just to give an idea of the type. And I think another very important aspect of teaching science, which in spite of reactions it continues to dominate discourse on science education, and that is development of scientific temper. Of course, one clear articulation came from Nehru, but there is a lot of discourse on it predating Nehru. Dewey talks of scientific habit of mind, and of course, he says that one of the only two articles that remain in my creed of life is that the future of our civilization depends upon the widening spread of the scientific habit of mind, and that the problem of problems in our education is therefore to discover how to mature and make effective this scientific habit. This is John Dewey stating his understanding of what he expects from science education. I think he says this in his book Democracy in Education. So, the burden on science education is not only to teach science, but to create a citizen with the scientific habit of mind. And if we engage with this issue of what is scientific temper, that again is a debate in itself, but let us accept that it is a commitment to the method of science as means of acquiring knowledge, promoting a spirit of inquiry. Well, there is a whole list that I have tried to, that I have garnered from various views, that people try to interpret scientific temper in all these terms. I am not going through it, but you can read it quickly. And then this whole question of what is science, an issue that teachers engage with, and this was a question posed to Feynman by a group of primary school teachers. He had been invited to address a gathering of primary school teachers, and they asked him to answer this question, what is science? And this is what he had to say: science is to doubt that what is being passed from the past is in fact true, and to try to find out ab initio again from experience what the situation is, rather than trusting the experience of the past in the form in which it is passed down. And that is what science is, the result of the discovery that it is worthwhile rechecking by new direct experience and not necessarily trusting the human race experience from the past. Well, if you trust Feynman, he is turning things upside down. He is saying that your task is not to transfer the knowledge that you have, but to create doubts about the knowledge that you have and recreate the knowledge. Well, you can see how messy it is getting for as science teachers, the expectations from us. Oh no, I pressed the wrong button. Sorry. Thank you. The no, it is just gone out of the. Okay. Yes. So, I think one question probably we should try to address and communicate with the science teachers is, what is this method of science that we are talking of? Since we believe that that is a very important goal of science education, to train our students in method of science. So, I have just tried to summarize what I have understood from reading so many philosophers of science and others about it, that it is material practice of science is based on systematic experimentation using evolved techniques and procedures involving observation, data gathering, analysis and presentation using mathematical methods. The method of drawing inferences uses analytical tools like classification, deductive or inductive logic, and probability and statistics to arrive at truth or falsity or the probability of certain hypotheses. The hypothetico-deductive method, deeply anchored in and based upon a structure of concepts related through an ever evolving theory and model building. Modeling of reality linked to theory presumes a world consisting of concrete, like objects around us, heavenly bodies, etc., and abstract, like force, space time, entities existing out there independent of the observer. The process of conceptual development and theory building is characterized by rational reasoning and critical inquiry, enabling evaluation of any claims, beliefs, assumptions and presuppositions or implications drawn from it. Naturalism as a basic assumption at the core of the scientific method, that starts with the materialistic conception, but goes beyond it to include whatever causally effective entities that science finds through conceptualization. Okay. I had great problem in formulating this statement, because one couldn't just say that science only accepts what is there, what we can see concretely. I mean, we deal in a lot of abstract concepts, and we play around proposing a lot of abstract concepts, and it is only eventually when we have a lot of experimental justification that we begin to say that this what we imagined is the reality. So, if you look at the way the concept of force has evolved, or the concept of electromagnetic field has evolved, I mean, or even concept of atom or genes, they began with some sort of an abstract formulation, and when we gradually built up a whole body of evidence, experimental evidence, the so called logical deductive method, logical determinism, and eventually today we tell our students things are made up of atoms, right, and force exists, electromagnetic lines of force exist. Your mobile phone is working because there are electromagnetic waves all around you that are carrying the messages to your phones and all, and we talk about all these abstract concepts as if they are reality, right. Testability and hence falsifiability of any theory as crucial touchstones of scientificity of any such process. Well, we owe this to Popper, this great emphasis on falsifiability of being the touchstone of any theory being scientific or not, that we should be able to formulate a hypothesis or statement which will falsify that theory, only then we will say that this theory has some scientific legs to stand on, right. This quote from Einstein, which he wrote in his foreword to translation of Galileo's dialogue concerning the two chief world systems, I like this quote a lot. There is no empirical method without speculative concepts and systems, and there is no speculative thinking whose concepts do not reveal on closer investigation the empirical material from which they stem. I like this statement because we have somehow got used to good science being theory, lot of theoretical. I mean, and the way all our school science teaching has got oriented towards preparing for JEE has meant that all the elite coaching classes tell you practicals करने की कोई ज़रूरत नहीं है, कोई एक्सपेरिमेंट वगैरह करने की ज़रूरत नहीं है, जेई में तो कुछ वो आएगा नहीं, you need to only just do your theory well, and they give the impression to the students कि साइंस में एक्सपेरिमेंट तो मतलब प्रैक्टिकल तो नंबर वैसे ही मिल जाते हैं, तो इसलिए एक्सपेरिमेंट करने की तो कोई ज़रूरत नहीं. आई मीन दिस इज़ द रियल स्टेट ऑफ थिंग्स, सो दैट्स वाई दिस स्टेटमेंट appeals to me, and I do want science teachers and students to mull over this, what they are experiencing as science education is actually not even half of it. It is a totally false version of science that our schools are teaching, where you do not see any link of experiment with the theories that you have learned there, unfortunately. I am making a strong statement, but I also feel very strongly about this. Okay. This is one statement which I know comes from heart of every student कि जो कुछ भी हो, अगर मेरे कॉन्सेप्ट क्लियर हुए तो मैं जेई भी कर लूँगा, और मतलब सीखने का मतलब है कॉन्सेप्ट क्लियर करना. एंड ए गुड टीचर इज़ जिसके कॉन्सेप्ट क्लियर हैं, वो क्लास में जब वो समझाते हैं तो उनके कॉन्सेप्ट बहुत क्लियर हैं. बट दिस आर्टिकुलेशन आई थिंक इज़ अ वेरी डीप आर्टिकुलेशन. व्हेन वी से कि कॉन्सेप्ट क्लियर होने चाहिए, विच डजंट मीन स्वीपिंग द concepts aside. A popular perception of good teaching learning. Important to clarify what do we understand by this and how to achieve it. What do we mean by a concept and what is its role in the construction of knowledge? How do common sense notions evolve into concepts and hence into deeper conceptual knowledge? What do we need to do in teaching of science to facilitate better conceptual knowledge? And how do we assess the level of conceptual knowledge achieved? I think these are really very important questions that emerge from the jumla of concept clear hona. Understanding concepts is to engage with analogy and metaphors used to formulate and articulate concepts. I think analogies and metaphors are very important tools in the bag of a science teacher attempting to convey conceptual clarity. Students comprehend concepts and theories drawing upon their familiarity with language used. That the language as it evolves in a communication between the teacher and student plays a very crucial role in concept clear karna. Use of idealization and abstraction to evolve concepts that are increasingly counterintuitive. There is a lot of research literature on this, the challenge of counterintuitive concepts that children begin to face very early. I mean, our present day knowledge that we live on a earth that is shaped like a ball, while everything around us looks flat, is probably one of the earliest counterintuitive notion that is pushed down children's throat, and they accept it without really realizing why to accept it. And there is so many counterintuitive notions that have evolved. I mean that we are going around the sun and the sun is not going around us, while every day we see the sun going around us. So, there is so many of such counterintuitive, in fact atomic theory is very counterintuitive, right. So, students' intuitive concepts and beliefs are challenged very early in the science class, and we pay very little attention to that. We feel this is something हम जब बता रहे हैं तो आप मानना ही पड़ेगा ना. And students also very early grow into जो टीचर कह रहा है और जो टेक्स्ट बुक कह रही है वही सही होगा. Problems faced in teaching draw attention to the role of culture, the role that culture plays in learning and practice of science. And this is one aspect which I think is drawing a lot of attention, particularly when we begin to engage with this issue of conceptual learning. Okay, I think I am done with trying to draw up some sort of a theoretical background to what I want to talk about. You think I should stop for a minute or two if there are any clarifications needed on what I have said, or should I just rush on? I think I will move on, because maybe what I have said in very abstract and theoretical terms will acquire some concrete feet when I begin to talk about the example, right. So, the example that I have chosen begins with the question of why seasons change, a question that children begin to ask, and at primary level we begin to think that, oh yes, children understand why seasons change. I know earlier primary school class 3, 4, 5 textbooks in EVS or earlier versions of science textbooks used to deal with this question at that age itself and nipta dete the. Now I find that in a curricula the science textbooks do not dare to answer this question, but they have left it to the social scientists, the geographers, and doing the other one. Yeah. So, this is chapter 3 of the social science textbook of class 6, and well, it is titled quite pompously, Motions of the Earth, and you will have to scroll this a bit for me. Yeah. So, as you can see, the opening line of this chapter expects a class 6 child to immediately understand the difference between revolution and rotation. Okay, and they are printed in bold, and what all is happening on earth is because of rotation and revolution, and then it goes on to explain what it means by rotation and revolution. But the most interesting thing is that they are already pointing out to this angle of inclination of 23.5 degrees, and this is the question that has tripped me for many years when teachers ask me which is this angle of 23.5 degrees. And then I realized that for a class 6 child who has just been introduced to angles, angles are something between two straight lines when they intersect at a point. So, which are these two straight lines which intersect at which point, which tells us that this is the 23.5 degrees angle. And well, I remember myself as a child wondering which protractor would have been used to measure this 23.5 degrees, and where was it placed, how was it done, or was there some other magic, or somebody found this out in his dream and then told the world that it is so. Well, this chapter talks about it, and if you go to the next page, and if you look at this diagram, I think this is a very revealing diagram. And why seasons change, a very common argument, and I have seen earlier textbooks which have stated that summer is when earth is closer to the sun and winter is when it is farther from the sun, and it is so intuitive. You sit around a fire, you know when you are close you feel hot, and when you move away you feel cold, right? But this diagram quite clearly says that when you are, I am sorry, I think the letters are not visible, but this diagram is saying that when it is far on this side it is summer, and when it is far on that side it is winter, and when it is actually close to the sun. So, actually the complex thing is that the children have to interpret what this diagram is about. Quite clearly a very exaggerated ellipse, but most of the science teachers have, and we also have all mugged that the earth's orbit around the sun is an ellipse. So, this sounds reasonably true, right? And yet टीचर्स वेरी क्लियरली से सब इससे हम ये नहीं समझा सकते कि ये आप ये भी कह रहे हो कि when the northern hemisphere has summer, the southern hemisphere has winter, and then you also say that the length of the day and the night also has some relation with change of seasons. Winters have shorter days, summer have longer days, and this it's same for the southern hemisphere walas also, that when we have short days they have long days, right. So, I mean many of those things are stated here, but the explanation is to come from this, and actually it is a diagram drawn with mixed perspectives, and we expect a class 6 child to sort that out, which part of the diagram is drawn from which perspective, and arrive at a cogent explanation of why seasons change. And this is a better version of a textbook. I have yet to see a textbook which has a better explanation than this for a class 6 child, but we move on. We think we have answered all the questions quite satisfactorily, and then of course we have the class 8 science chapter, which Sadhana also referred to yesterday, about stars and the solar system. And I regret that, I mean people who wrote that chapter have been my gurus, I've learned from them a lot, but I regret that the title was so promising, and unfortunately the chapter totally becomes a heavily information loaded chapter with serving no purpose in terms of theory formulation. How did we arrive at this picture of the solar system, and this whole question about that just about 400-500 years ago the whole world was believing that earth is the center of the universe. God has created earth for us human beings, the best creation of God, and hence we have to be at the center of the universe, and everything else has to all the time हमारी परिक्रमा करना चाहिए हमारी सेवा में, है ना. So the sun does that, the moon does that, the stars do that, and this was the official, I mean the version of what the universe was like till about 400-500 years ago. And if anybody in those ages was foolish enough to challenge this and say no, earth is not at the center, God help that individual. I mean there are incidents in history of people who were burnt at the stake, or there is this very moving incident about Hypatia, the famous mathematician, lady mathematician in Alexandria, who was dragged alive behind a chariot. I mean that is what history tells us, and killed for her views. There are a number of such stories. Of course, and we also know that Copernicus, whom today we say was the person, and we use his name to say the Copernican Revolution. He was somehow convinced that Earth is going around the sun, and so are all the other planets, and he wrote all that down in his book. I think he called it On the Revolution of Heavenly Spheres. But he kept that book to himself, and when he was on his deathbed, he released that book saying, "Mera aap kya kar loge? I am about to die." But he probably himself didn't realize what a revolutionary idea he had floated, and of course those who followed him also suffered for supporting him. This was the struggle of science being born in a new way, a very significant event in evolution of science. But our chapters miss out on that very significant event and understanding the way it all evolved. So I think we can go back to my slides. So I have been trying to explore how this can be done, firstly with teachers, and through the teachers with students. The question that was raised yesterday, at which age this would be an appropriate thing, but I would take some time from you to just take you through the steps of that journey, and then maybe we can get back to discussing all these. So how do I begin that story? Well, the story will have to begin by first answering the question, what is the shape of Earth? And it has been written about very interestingly by Asimov, the whole story of how we came to believe that the Earth is round like a ball and not flat, not like a flat dish with its edges raised so that the water doesn't spill out. I mean, the human race went through such conceptualizations, such idealizations, such model building before it finally arrived, that the Earth was shaped like a ball, and we are all standing on that. And even today, you just open up any teacher training class or a student's class to questions, one of the first questions that comes, सब ये बताइए कि हाँ हम बॉल पर खड़े तो हैं, ये तो समझ में आता है कि he who has the privilege of standing at the north pole is all right, he is in a stable position, पर हम लोग गिर क्यों नहीं जाते हैं और टेढ़े खड़े होते हैं, पर we don't even perceive, otherwise our whole body balance system is so sensitive कि if the floor shifts a bit we can perceive it, and yet you are telling me that standing on this round ball we don't perceive that. And what is this ऊपर नीचे, तो उल्टे भी खड़े हुए हैं लोग, आप कह रहे हैं. And we are back to this question कि why doesn't the water in the oceans empty out? What holds it there? Very valid question, easy to answer. You know what that Newton he told us, gravitational force उसके कारण होता है, and after that there are no further questions. We have a very clear cut answer, but I'm sure it leaves a restless mind. So from that point onwards, of course, these two slides, I mean, I showed you what is there in the NCERT textbooks. This is from one of the most popular online tutorial sites, very popular these days, promoted by the most famous actor. So which of the following is a possible cause of change in seasons? The answer is the axis of rotation of the Earth is tilted with respect to the plane of the orbit. So if you can explain this to even a class 10 child what this means, I think it will be a good. So just a bit back and forth. It is not a question which is so easily resolved even by the best minds in our country. Okay. So, where do I begin the entire story? I think we have to begin first by talking about shadows, and the conclusion that human race drew from its analysis of shadows about a very abstract concept which we give children very early, that light travels in rays, light travels in straight line. A very fundamental and important concept. But if you begin to think that if I look at shadows, does it immediately jump on me that, oh, I see the light traveling in a straight line. प्रकाश सीधी रेखा में गमन करता है. All the Hindi medium textbooks have this phrase, which is almost a definitional phrase which every child has mugged up. But yes, I think it's a very important concept which we have to help every child to articulate graphically also how a shadow is being formed. We have these diagrams, but the interesting part is that those diagrams show less and hide more. Why do I say that? Because actually from any light source the number of light rays coming out is really not countable. But what our diagrams do is they very selectively take one or two rays, very wisely select one or two rays and draw them and show you that this is indicative of what the other rays would be doing, that within this range these rays will be stopped while the other rays will keep going, and that is why the shadow is being formed. So, I have had very interesting encounters with teachers. Okay, why don't you show all the rays? Okay, I said I will show you all the rays. So, I draw. Oh, ये तो आपने झाड़ू बना दिया, इसमें तो कुछ समझ ही नहीं आ रहा. So, immediately we begin to understand, yes, this whole idea of ray diagrams itself is an idealized construct. It is an idealized construct of an abstract concept, and yes, we need to spend some time with these young children to help them come to grips with it, with a number, and they come to grips with it. I am not saying that it is difficult, and that raises a doubt in my mind. All these cognitive theories which say that your children's ability to grapple with abstract concepts is age dependent, and etc. I feel that range is being stated too precisely, because all such experience of shadows with children and how they derive their own, in a sense they construct their own knowledge of what is happening in causing shadows. But that is a very important conceptual understanding or a mental model to arrive at to begin the whole story, because light rays are coming from the sun to the earth, and understanding how they are distributed is fundamental to understanding why seasons change. So, the next step is an equally important idealization, that the rays falling on earth from the sun are parallel. The diagrams that explain why seasons change are built on this assumption. So, if I go back to the figure that was there in the NCERT textbook, no, I think you all remember that, it is very cleverly showing only parallel sun rays coming from the sun, but the sun that they made is of such a size, and the earth that they made it is of such a size that it is difficult to understand where the other rays are going and why the jhadu is not there and why only parallel rays are being selected. And the answer to that lies again in a very simple model building exercise, which I found to be very effective with teachers and children, but it suddenly tells us that our textbooks are fooling us. And I have done this exercise here. Basically, let's draw a two-scale model of the solar system based on the data that we have today about the size of the earth, the size of the sun, the size of the moon, and the distances between them. And I have taken a scale of 100,000 kilometers is represented by 1 centimeter, and it's nice to do all these calculations with children, because as each one of them is revealed, it also helps them revise their middle school mathematics. So on such a two-scale model, the earth would be a sphere of diameter 0.12 centimeters, that is just slightly bigger than a millimeter. So if you imagine a round thing which is just about a millimeter in diameter, बच्चे के दाना राई का दाना, सरसों का दाना, राई का दाना, that's roughly the size of earth in my this model. The sun will be a sphere of 13.92 centimeters, about 14 centimeters. So my 16 scale is 15 centimeters. So a baseball, maybe it's not a football, it's not a tennis ball, somewhere in between. The best analogy is kharbuja, watermelon, a medium sized watermelon of this size. So this is my sun, that rai ka dana is my earth, and of course the moon is very difficult to spot. It's about a tenth of 0.017 centimeters. So that's about 1/10 of a millimeter. So I think it helps us say, okay, just the tip of a pin, probably that is the size of the moon. The distance earth to sun is about 14.96 meters. So I am sure everybody here has an idea how much a meter is. So if my watermelon is here, the rai ka dana would be out of this hall, right? And the moon would be that pin, small tip of the pin orbiting in a circle which is 3.82 centimeters radius around that rai ka dana there outside this hall. This roughly is the picture, and if you ever have the privilege of going up out of the solar system and looking down, this is, you can now imagine what you will see. Yeah.
How do you convince the students that these figures are accurate? I mean, they could equally invert the question and say कि आप कह रहे हैं कि parallel होगा इसलिए आप बना के दिखा रहे हैं कि
that is a very interesting question, and I find I have to take a digression there. The digression is given to me by this diagram. This is Eratosthenes' estimation of the circumference of earth and hence its diameter. It's very simple geometry, again parallel light rays. I don't think I need to spend time on explaining this, but I find that students and teachers get very excited. Oh, so this is how it wasn't that somebody took a very, very long rope and went around the earth and measured its length. And this Eratosthenes did somewhere around 300 BC or something, right? So, and it needs geometry that children do around class 8, class 9. They need to, where they do geometry of circles and parallel lines. There is this, people immediately, alternate angle, or is it the corresponding angle that is equal? I think I don't need to spend the time to explain how Eratosthenes did this, but the moment a student asks this question, the teacher can immediately unleash this and tell them that this was the beginning. Of course, there were more developments on basis of which we now so confidently say that this is the distance between the earth and the sun, and this is.
Eratosthenes is still assuming parallel lines, so it's sort of you're using your presumptions to.
Yeah, see, people at that time had already arrived at this concept that sun rays from the sun on earth are parallel. And how would they have come to that conclusion? Again, playing with shadows. If I have two poles apart, if the sun's rays are converging, what would the shadows be? If the sun rays are diverging, what would the shadows be? What do you actually see as the shadows? And that is what, but there is a very important mental jump about, which is of generalizing from a very specific, right? I don't think people at that, I think children also begin to appreciate how early such difficult conceptualizations and conclusions were being drawn by people. They did not have this Kharbuja and Raika model with them at that time. I am using that now to convince you or the children that that is why all the light rays from this Kharbuja which are falling on that Raika Dana, the Raika Dana can only perceive them as being parallel. But then I also have to let out the secret that when we will talk about eclipse, I will again tell you that no, they are not parallel, because my explanation of eclipse fails if I only use the assumption that they are parallel. And this is what method of science is, which we need to help our students to appreciate, right. So, this whole idea of idealization to understand a phenomena, to explain a phenomena, and come pretty close to explaining what we actually observe. And yet when it comes to analyzing eclipses, when we have to explain umbra and penumbra, the parallel rays idealization has to give way, right. The point is, children are very indulging. When you tell them, look, this is how science was done and this is how science is done, then acha, ab samajh mein aaya. So you're immediately withdrawing from a position of authority. Ye aise hi hota hai. You're already giving them a taste of how flexible science is in understanding such concepts. And these are very simple things. But your question was posed to me very early, and I only found this way of tackling it with students of class 8, 9th level who can understand the geometry that Eratosthenes used, and they also appreciate the beauty of what Eratosthenes. Kya dimag tha yaar, I get this remark. So, a very important step, but a science teacher who can do this, I am sure you can imagine the type of, वो कहते हैं ना कि पूरी क्लास को ग्रिप में ले लिया. For a good science teacher, क्लास उसके ग्रिप में रहती है. I mean, these are phrases that we hear from children and teachers. And so, but I mean, we are only part of the way to building up a whole theory and model. Now, this is an exercise that I do, and I am presenting it in as rough and crude form that it actually gets done in a classroom, because I think I and most teachers are just as good as this in their drawing. But I think when I build up this diagram, each step the teachers or the students that I am doing it with, they go along with me, appreciating and understanding what I am talking about. So, I say now there are many things involved in this. Firstly, the picture or the data that I am sharing here in this picture is not a one point data, it is not a one time data. That this sort of understanding or this picture would have evolved over a very long period, over generations of people traveling over the globe, and looking at how the shadows of a vertical pillar changes over a day, over the experiment that Sadhana talked of yesterday, over different days, gradually over the entire year, and what is the picture that emerges. So, I will just try and deconstruct this for you. I hope it is not looking too confusing. Well, what this says is that we are all familiar with the equinoxes and the summer solstice and the winter solstice, right. That firstly I have drawn this circle and saying this is earth, and then I say yes, we have a line which we call the equator, which is a line. How did people find out that this must be the equator? An equator means something that divides the earth into two equal parts, and how did we find the equator? I think the most plausible explanation that I have is that at almost all places on earth, and this means that whoever came to this conclusion already had tools of measuring time, at least in a very crude way. So, length of the day and length of the night, and that at some point people realize that there are places on earth where the length of the day and length of the night is the same on every day of the year, and that the locus of such points, the line joining all such points, is the equator. People realize that that was a continuous line, a circumference around the earth. Now, quite clearly people did not go on every point and measuring it. This must have been a generalization of a very high order, because there are points which were in the ocean, there are points which were on continents yet to be discovered, and yet you can only marvel at the generalization that and there is no single name who did it, but how did the concept of equator come about? This is the most plausible explanation that I have come across. Why? Because if you go north of equator, the ratio of day hours and night hours changes across, except that there are 2 days in a year on all parts of earth where day and night are of equal length, and we call them the equinox days, and they are 21st March and 23rd September, right. And then there are the summer solstice and winter solstice, and this is where the interesting 21.5 degree angle pops up, and nobody knows why it was that was not even 21.5 or 23.5, it was 23.4 something which we know now, and that the sun rays from 21st March seem to keep shifting to the north till on 21st June we reach a point when the sun rays are directly perpendicular overhead at another place, and the locus of those points we call the Tropic of Cancer. And similarly on the south there was another Tropic of Capricorn, and all this data tells us that the sun in the sky seems to keep going around in this about 47 degree angle all the year round. So, if every day you are looking at the position of the sun at midday, in fact before saying all this, I find posing a question very interesting. When is the sun overhead exactly? At noon time. Every day? Yes, every day at noon time the sun is exactly over our head. Are you sure? Yes, shirt लगाओगे? नहीं, shirt नहीं लगाएंगे. But you know, this conversation is very important, because what does it do to us? You know, we have such notions about things happening around us which we never cross check, and science is forcing you to cross check such notions. That if I tell you, ask you what happens in Pune, how many days is the sun directly overhead? Directly overhead. आप तो पहले से पढ़ के आए हो. So, and if I ask the same question in Udaipur or in Delhi, the answer is on no day. Never is the sun overhead. And you tell a Delhi wala that in this peak summer time, रोज तो इतनी तेज सूरज की गर्मी लगती, इतनी तेज धूप होती है, और आप कह रहे हैं सिर के ऊपर नहीं होता. So, you know the significance of the 23.5 days, and to tell the students that, you know, it is so precisely measured now that if you go to Bhuj, the road going into Bhuj, just outside that on the road a line is drawn and there is a board saying this is the Tropic of Cancer, which means our PWD, the road making department, is telling us that the sun just comes overhead at this point and then goes back. It does not go beyond this point. I know there is a similar line on the road going from Udaipur to Ahmedabad, and it comes a few kilometers after Himatnagar, again drawn on the road. There is a similar line on the road going from Vidisha to Bhopal, near this station called Salamatpur. In fact, at many places near Ranchi also there is a line. And when you tell children that अगली बारी आप कभी भी ऐसी जगह जाओ तो ज़रा रुक के देखना कि कहाँ पे है, and then you look at it on the globe or on the map, and the Tropic of Cancer acquires a totally different meaning for you, and so does the Tropic of Capricorn. But to, you know, now visualize that apart from this myth that we are told that the sun rises in the east and sets in the west every day, and then you begin to correlate that does not happen. You know, even the point at which the sun rises every day is spread across a 47-degree angle. I know it now very well because my house in Udaipur faces west, and over the year I can see how the point where the sunset really goes from here to here, and you just have to think about the window through which the morning sun comes in and how it changes across the season, and suddenly, you know, all those poems about sun rising in the east and setting in the west, etc., become suspect, right? But what does it tell you? Okay, now if you have to visualize how the sun is going around the earth, so there is one movement of the sun which every 24 hours it is rising in the east, setting in the west. And if you begin to think that, you know, maybe earlier people thought that every day a new sun rises, but you say no, now we know that it is the same sun which goes under us and then comes back. How did you reach this conclusion? Well, I think that is a reasonable question from a child, which we should at least help the child to resolve these type of things. But that sun is not only doing this every 24 hours, but over the year it is doing a sort of a dance, you know, that half the year it is going from south to north between this, you know, Tropic of Capricorn and Tropic of Cancer, and then coming back rest of the 6 months. And this is what Dakshinayan and Uttarayan is, and people say, अब समझ में आया ये जो उत्तरायण और दक्षिणायन है उसका मतलब क्या है. And this is what this diagram is showing. I have used different colors to show the same sun rays. The green ones are the sun rays coming on the summer solstice day, and the blue ones are the winter solstice day sun rays, and the green ones are the red ones are the the equinox days. So, in fact, this static picture is showing a dynamic phenomena, what happens over a year. And that is another aspect that children begin to realize, that you can use static diagrams to show a dynamic phenomena and convey a sense, right. And of course, now from this I will not do it here, but we begin to understand how the length of the day changes throughout the entire year, how at the poles there is 6 months of day and 6 months of night, and I think I am running out of time, but I will just fast forward from here. But this leads us to of course, now to this one can add what is the movement of the moon, and how can we visualize the movement of the moon, and then the movement of the stars, and beginning to appreciate why pole star is so important. And that any statement which says that stars also rise in the east and set in the west is a total myth. And that from that going to how do you think now people at that time visualized what the universe was like, and that those models were, what did people visualize? They said, oh, I mean the Aristotelian picture basically was that the earth seems to be at the center, that we can't dispute yet. So, the sun is on a crystal ball, it's embedded on a transparent crystal ball which we cannot see, and it is very far away, and that crystal ball, whosoever controls it, has a motion which goes from east to west once every 24 hours, and that causes day and night, and that the same crystal ball while going like this in the north south direction is doing this dance over with a time period of 1 year, and that is what is causing the seasons to change. And that now if you have to also show the movement of the, include the moon in that model, moon can't be on the same crystal ball as the sun, because then it will have to go at the same pace as the sun, which it does not. So, we have to visualize to imagine another crystal ball which has moon embedded on it, and it is roughly going in the same way as the sun, but no, does the moon also do this north south dance or no? Now, there are all those interesting questions which arise, but yes, this is the imagination that ruled the human mind for centuries, except that they kept adding crystal balls. So, there was this crystal ball which had stars embedded on it, and the rotation of that crystal ball, the axis was through the pole star, and they had spent many sleepless nights tracking the various stars, drawing up a map of the skies. And as children we were always fascinated by that riddle, the ulta thal motiyon se jada, moti usse ek na gira, that the stars in the sky were a dish in which all the stars were embedded, and you are suddenly telling them, no, that very interesting paheli that is there in the Hindi heartland, which children learn very early, batao kya hai ye. So, no, it is not a flat dish, it is a crystal ball embedded with all those stars and is revolving around an axis which goes through the pole star, and suddenly the whole thing begins to make sense. But this was science of that era. Of course, the questions were there, where is this earth resting? We had all these mythologies about earth resting, और शेषनाग के फन पे है कि एटलस के कंधे पे है कि वो कछुए के पीठ पर है. We had all those stories, but nobody really took them very seriously. I think people were not satisfied, and they were still looking for answers to such questions for many centuries. So, give the children a sense that what you are being told now is not something which just we knew the day we were born. There is a lot of thinking, lot of analysis, lot of data, lot of imagination which has gone behind it. And then comes the turn of planets, that suddenly during all that observation people were finding these 4 stars in the sky, which were actually, the term means avara, किसी भी तरफ चल रहे थे, मतलब all the stars are going in one direction and these suddenly shift their movement, and this movement was not visible in a day. I mean, this whole idea of understanding retrograde motion of planets was so crucial, and the type of observation that it requires, painstaking observation over days to plot the skies and to plot the position of the stars, to measure the position of the stars. But by about, Ptolemy, who is about 300 AD, had very detailed charts of planetary motions. So, which means people many years before him were already plotting all that, and this whole notion of retrograde. So, how do you make children appreciate this retrograde motion of planets? My experience is that if you have gone through all that, tracking the sun and tracking the moon, children begin to appreciate the type of observations that were required to arrive at this concept of retrograde motion of planets. And there were 4 that we could see, 4 of them that we could see with the naked eye. So, the sun, the moon and the stars and the 4 planets, Venus, Mars. Mercury we couldn't see easily, it didn't come in people's perception for a long time. So, it was Mars, Venus, Jupiter and Saturn. And so, the 7 heavenly sphere model, the 7 crystal ball model was there, and how would because each planet had a different retrograde motion, so each had to be given a crystal ball of their own, and hence those 7 spheres. And there are beautiful models which which are there in museums in Italy and other parts of Europe, well preserved, that this was the way people thought the universe was at that time. I am just trying to fast forward the theory, but how the retrograde motion of planets, explaining that, and from Ptolemy to Tycho Brahe, a fairly long period, more than 1000 years, the type of painstaking observation, and the Tycho Brahe for the first time saying that this whole retrograde motion explanation is becoming too complicated and it is still not accurate, and then saying that maybe what is happening is that Jupiter and Saturn and the planets are going around the sun, and sun with this family of planets around is going around the earth. So, we are moving for the first time, people begin to, at least somebody proposed that possibly not everything is going around the earth, they are going around the sun, but the sun still goes around us. And then from Tycho Brahe, Copernicus got his cues and secretly wrote his book, not daring to publish it, and the Copernican Revolution took place. And the model that Copernicus gave, what did he have to think? Because he would have to explain both these motions, the daily motion of the sun and the other planetary bodies, the 24-hour motion, and also the annual motion and the retrograde motion of the planets. All these observations, of which now there was firstly a whole lot. Secondly, people had already fairly complicated mathematical formulations to predict, and the motivation to do that was because our astrology was connected with that. So, there was so much of effort in developing the mathematics which would sort of formalize the movement of all these heavenly bodies and predict and the excitement when those predictions were fairly precise, and the frustration when they were not, and hence trying to improve the model, like a continuous process which eventually leads to Copernicus totally overturning the geocentric model and proposing the heliocentric model. I will just take 5 more minutes, because I think the important thing was that what did Copernicus have to do? He had to tilt the earth at an angle of 23.5 degrees. And where did he get that 23.5 degrees? Oh, it was from there, from the geocentric model. 23.5 degrees was already there with us. It was Copernicus' genius to suggest that, if earth has to go around the sun, and if it is rotating on a vertical axis to the plane of the orbit, we will not be able to explain all this, and that if only I tilt it at 23.5 degrees, and then realizing that this 23.5 degrees angle, my globe, if I am the sun and the globe is going round like this, it cannot be that the tilt is here like that. And I hear many people say 23.5 degree सूरज की तरफ झुकी हुई है. You suddenly realize नहीं यार ऐसा तो नहीं हो सकता कि if it अभी ये मेरी तरफ झुकी हुई है तो ऐसा नहीं होगा कि it can go like this. So when you are handling a globe, you have to be very careful as a teacher, that how will you take the globe, show the children that here is the earth, और मतलब एक बच्चे को आप खड़ा कर दें सूरज के, then you take this around like an आरती, नहीं चलेगा. It has to be according to the principles that you have understood, that this, if this is the tilt that you are starting with, it will stay like this all the year round, which means in the entire orbit, and that is what then relates to that diagram in the. So once you do this globe going around the sun, then children can appreciate that diagram in the NCERT book. But it is very crucial for every teacher to understand how to handle a globe, what to do with this tilt, because then only the explanation. And the simple thing to do is that when this is going around, you are only duplicating these motions of the sun as seen from earth. That here this person standing on the equator here, at this time the parallel rays are perpendicular on the Tropic of Capricorn. So this is the winter solstice, it is winter in the northern hemisphere. I think you all get the hang of the story, but I think I can only say is that this whole process really takes us through this fascinating story, this fascinating development of going from geocentric to heliocentric. Of course, there are further stories, as Galileo is born after Copernicus and somehow takes it upon himself to convince the world that Copernicus was right, and he pays for it heavily. He lost his professorship, which at the University of Padua, and house arrest and all that was there, but he kept saying, but yet, I mean, people tried to convince him, you just say that this is a mathematical construct to explain things. It actually says, but the earth does go around the sun. He was so convinced about it, right? And the year Galileo dies, Newton is born. So you see, as you can see, so a sort of stage was set for the Galilean-Newtonian revolution to take place, for physics to totally transform itself, for science to transform itself. And I just will end by saying that I feel the NCERT chapters missed the opportunity of narrating this wonderful story of science with all elements of method of science, which I tried to point out. They missed out on that opportunity. And if somebody can write it won't be one chapter, I think it will have to be more than one chapter. But this whole story needs to be told to the children. Of course, we will argue which class, which year, which age children will be able to appreciate this whole thing. That continues to be a challenge, but I somehow feel this is a task yet to be done. And I will end by saying that I hope the Department of Science Education will take up this. And it's not only this geocentric to heliocentric theory, but there are n number of theories. I mean, we convinced Bhaas to write about the heat and temperature story, and he did a wonderful job of it. I would like you all to see that very small booklet written for teachers, because I found in all trainings people are messed up about heat and temperature. What is heat and what is temperature? And that if I have water in 2 mugs and this is 50 degrees and this is 60 degrees, if I add them, will the temperature of the mixture become 50 plus 60 or kya hoga? And how will the heat add up? And I find teachers are totally confused on this. I mean, any area you take up, cell theory, Mendel's experiments and the beginning of genetics, Newton's, I mean, the concept of force, atoms and molecules. I mean, everything has a very interesting story behind it, and science is that story. But then we need to be very careful, that story must reinforce all those things that I said earlier. So I am hoping that all these young scientists, they will come forward, and apart from other things that they do, they will take up one such area and do this, and that will make science education, at least at school level, a totally different experience for our children. I think I will stop here. I have taken about an hour extra. Or comments.
So, no, it's okay. This is probably the harder part to teach, but compare that with the easier part, which is just convincing them that the earth is round in the first place. How long does that take, and how do you go about that?
Actually, with this, the way the story is told by Asimov, and our colleague in Eklavya did the Hindi version of it, Aakhir Prithvi Gol Hi Nikli, Deepak Verma, you will find that article in Sandarbh, the magazine, the resource magazine for science teachers that Eklavya publishes, and I think there is a Marathi version of it also. Getting children to read that story and understand, I find even class 6 children, it takes about a week for them to appreciate that, reaching this conclusion that we are on a world which is shaped like a ball. They begin to appreciate that. I don't know how long it takes for them to digest that or to accept that, but they begin to appreciate why that is being said. And it also gives them this idea that these questions are valid. कि जैसे मेरे को दिखता है वैसा नहीं है. And this is science. I mean, this shakes you up, नहीं तो we are brought up with this philosophy of प्रत्यक्ष को प्रमाण किया. No, जो हमें प्रत्यक्ष दिख रहा है उसके लिए प्रमाण थोड़ी चाहिए. That is obvious. And suddenly we are telling children, I mean, without even saying this is what rules our mind in the early years. And one of the first destructive things science does is that this is not necessarily true. The nature plays games with you in many ways.
Thank you for a wonderful discussion. It's quite enjoyable. I have sort of broader comment or question basically, that in most of the schools we go out, in fact, fine, there are some good schools, but most of them are really these private schools, and teachers, especially the junior ones, are essentially part-time job, right? Most of them are not even trained, and immediately after the school they have something else to do, because they have to really have their ends also meet. and there's not enough salaries and all that, right? So to expect the teachers to spend that much of time what they are going to teach tomorrow, even if you provide the material, it's quite difficult. Right now they don't have the material. As you said that somebody has to write up this also. Right? So how that problem can be addressed? I mean, what do you think? Because you have a lot of experience dealing with the low level. I mean, I have seen the schools around the Udaipur area and Jaipur area. Not that much in Pune area, but I'm definitely sure about those, that what the challenges are and issues are.
You see, when discussion turns to such issues, we really don't have any answers. So, वो तो मतलब अंग्रेजी में कहते हैं ना that if you will give peanuts, you will only get monkeys.
We have a lot of us here, right? And so hopefully this is right time to start bringing up these questions, right?
Yeah. But you know, I'll also try and show the other side of the coin. Whenever I have had workshops, there are teachers with all sorts of backgrounds and levels of professionalization, training, etc. But one common reaction that I've got is कि ऐसा तो हमें कभी नहीं करवाया गया और अब हमको सोचना पड़ेगा कि हम बच्चों के साथ.
That's exactly my point is.
है ना? Of course, I think there is a whole lot of questions that we need to ask the system or ask ourselves as being part of the system. What is the education ideal that we are aiming for, and what are the bare minimum essentials of the system that need to be built into it to be able to achieve that. Okay. But again, the questions are not so easy because you know it is so obvious. I mean, the political leaders immediately get back at you with कि it is the private school teacher जिसको हम इतनी कम तनख्वाह देते हैं उससे तो हम पूरा काम निकलवा लेते हैं और हमारे सरकारी टीचर जिनको हम ज़्यादा पैसे देते हैं उनसे काम नहीं निकलवा पाते. So you know those dimensions of the problems are of a different nature. I would say at some point, even for our own sanity, we'll have to draw a sort of a line between these two type of questions. One is basically around the question of what we think is the ideal approach to teaching science. That is still not a resolved question. It is a contentious question, but a question that needs a lot of engagement and gradually to arrive at a consensus. I mean, the consensus that we have now also is not a consensus arrived at or dictated by somebody and we totally. So, the need to improve our consensus, evolve a new consensus on what is our ideal of good science teaching is there. How will we achieve that ideal and what are the pragmatics of it, what are the problems preventing that, what are the factors preventing that, that is again a very rich discourse, etc. But you know, when we are discussing this, if we bring in these questions, then this discourse gets totally distorted. We need to be very aware that you know that this demarcation we need to maintain in our discourse. When we are discussing this, we need to you know really come to grips with the problem. Of course, there are consequences of being too articulate about this system, but yet somewhere that all those issues need to be raised. The answers on both sides are not easy or obvious. We really need to work towards analyzing the situation, understanding the problem deeply and trying to find the answers. So, I will totally refrain from saying that I know what is the solution because I have been in the field for so many years. No, I think what I have learned from so many years is that it is a very, very complex problem which I also do not understand fully, and it will be very stupid to you know say that oh, I am an experienced person, I will give you the solution. No. That is not so. But we need to recognize that there are these two domains which have their own set of questions and need a very deep discourse.
So, I have one more question which might be again of similar types but not on the system. So, it's more of like, I mean after especially in the last few years I have hearing these terms pedagogy a lot, right. Now, when we are talking about the kids of this age group like 4 to 5, 6, it's fine. But at some point, the rigor has to come in picture. The
Yeah?
rigorous formalism
Okay,
and the
yeah,
skills, they have
yeah.
to come in picture, right?
Yeah.
So even at ISER, I sometimes hear this pedagogy a lot. So, I mean, is there any sort of comment on that? Like, where do you sort of start differentiating? I mean, all these things.
Actually, in
what
some
we-
ways it's a continuum,
Yeah.
but see, my feeling is that particularly at school level, we are tending to oversimplify things. When we begin to say activity based teaching is the solution, etc. Because science has both these equally important aspects, the what Einstein calls the empirical aspect, where you do a lot of activity, experiment and rigorous activity. I mean, it is not just all joyful dancing and activity around, it is all very rigorous, painstaking work which leads you to these type of formulations, right. But there is great joy in that hard work, and the assumption that theory to ऐसे ही हो जाएगा, because good didactic teaching is equally needed in good science teaching as experiment based teaching. We have somehow come to plagiarize didactics. लेक्चर देना, वो लेक्चर बहुत झाड़ता है, पर एक अच्छा लेक्चर देना भी आना पड़ेगा ना. आई मीन एट सम स्टेज स्टूडेंट्स नीड अ टाइप ऑफ लेक्चर. आई मीन हम कहते हैं कि हाँ यार फाइनमैन लेक्चर्स देख लो एक बार तो समझ में आ जाएगा कि अच्छे लेक्चर का मतलब क्या होता है. But that is of course simplifying. But yes, I think that question is definitely there. What is good didactics? Interestingly, in some of the European universities there are the departments of education are called departments of didactics, particularly in Germany. Somehow there they seem to recognize that didactics is a very important aspect of science education, and hence all these pedagogical theories which seem to valorize activity based learning, discovery based learning, they seem to tilt too much on one side. We somehow need to restore that balance.
Okay, so my question is, should we study science in a historical way and develop concept from it, or should we study it in a conceptual way and try to use it in application? Because what I found is, studying science in historical way is more engaging. Like we come to know how the concepts are developed and we feel ourselves more engaging, but it's more like a storybook or novel. We just read it and cannot use most of it in applications. But on the other way, studying it in conceptual way is very boring. Like you just study the concepts direct and you do not know how they develop. So which is the better way?
I don't have the answer. I made this presentation today to see how you react to it. I really don't have the answer. But yes, we all have faced this challenge, how to engage children with concepts and make it a good engagement, not something that will make them run away from science.
So like Pythagoras theorem is such an important theorem in mathematics. Is introduced in 9th standard. Newton's laws are introduced in 9th standard. Even Ohm's law is like taught somewhere in 9th or 10th. Like these are something which are like very much fundamental to understand the nature. Like, don't you think that it is too late to like teach these things in 9th standard?
Well, my response to your question will only lead to a greater debate. But I think the outline of the debate is that early years of science teaching need to have a stronger empirical content in it. That's the age when some of the early years of science are in a sense relived by our children, and for some reason, I don't have any justification of it, but Ninth class suddenly seems to be the Rubicon where you make the jump and you become impatient, and now it's time to train our children in Galilean-Newtonian science. And that is what you see in the way the curriculum is formulated for class 9. You suddenly have to introduce Newton and his laws and the theoretical development of science which took place in this phase.
Yeah, so I have a question regarding, like, it's also from my school years. So regarding the flat world map, so like in my school years, I saw that the size of Greenland is almost the same size of Africa. So I had a really doubt about this, like why this is, and later, like after, like in my after 12th or something, I could understand that now this is actually the flat thing is not the same as the globe and something like this. Could you please like say something?
You see, I say that this is fundamentally a problem of being able to translocate oneself. You try this with different groups of children and even teachers. Which is the north direction here? You will get so many hands going up like that. This is north. It's again a problem of translocating one's mind to understand what that flat map on the wall is telling. And that's a very essential part of training which our science training, science education misses out. But it's so essential to, even using these tools like maps and graphs and things like that. I am amazed the number of times I get that this is north.
Yeah, you use this term didactics. What exactly does that mean?
Well, it's a more sophisticated term, but I have simple, crude explanations. It basically means that I have some knowledge which I want to transfer to you. So I make you sit down and tell you this is knowledge. This is like this. So it has a strong belief in a good one-way communication, but of course the premise is that one-way communication is very strong, very motivating, very communicative. Somehow the person who is making that communication understands the right level at which to pitch it so that the audience is with him all along. But there is no attempt to make the audience or the learner or the listener become an active. I mean, all the critiques of didactics basically say that you make the learner passive, and that the only way out of it is to make the learner active. So the didacts say in turn that good didact means the learner is active in the mind, even if he is sitting still in the benches for an hour or more. It has to be active in the mind.
Thank you. You had mentioned earlier that young students' intuitions are challenged very early in the science class, but often the process of the challenge and the revelations are disregarded by their teachers, who just throw facts at them, like you should know this. For the teacher to be able to take care of this, it seems to be a tricky balance, that to ignore it is to risk imparting wrong ideas because of a teacher's existing models of understanding differ so much from that of their students. But to try to take care of this seems to require so much deliberation and thinking. Well, I'm not asking for for one blanket answer, but in cases where teachers find themselves in a position where they are tempted to offer a lot of information in response, what things should they look for, try to be aware of in a student or in the situation that they are in, so that they don't end up shattering this view shaping process of the student?
You see, your question is touching a very perennial contradiction that teachers face, not only in sciences but in all subjects, whether it is languages, about spellings and all that. I think the present state of wisdom is saying to all teachers, give up your sense of insecurity that if I don't correct this child today, he is going to carry on with this mistake for the rest of her life or his life. That each one of us has tremendous capacity to realize our own mistakes and keep correcting. That is what learning is all about, right? To give yourself, the teacher, this great role that if today I let this mistake pass, that is the last chance. That is a very wrong understanding of how human beings grow up, and learn. So, I think the understanding is that the teachers need to have faith in every child, that which does not mean that you will say that if you are making a mistake, or you say, of course you are making mistakes, I also make mistakes, and we continuously need to learn to spot our own mistakes and keep correcting them. In fact, the ideal is not to rely on a teacher to keep correcting you. The ideal is for you to become wise enough to अभी अपना मिस्टेक पता नहीं चला, पर बाद में पता चल गया तो ठीक कर लेंगे. So I think this insecurity about wrong knowledge going with children, it does not gel with the versatility of human mind, which continuously keeps correcting itself lifelong.
Thank you.
Continuing to this only, isn't it also true that when children are young, if there is a statement that they hear from someone, it gets ingrained into their mind? So if such an approach is used, where if they get something wrong and the teachers just let it go for the time being, expecting that they will know it later, won't that give like a very strong rise to misconception from an early age?
That is why I put in that quote from Feynman. What he says is science. To question what is given to you as knowledge, that is doing science. That is a very interesting view on what is science. To give every human being, every child the confidence to question what is given as, to question all given wisdom and recreate knowledge for oneself. And that comes pretty close to what constructivists are talking about, and this whole ism of constructivism that is dominating science education and all education discourse at present. But I think what Feynman says has a ring of appeal in it, at least, if not truth. So, if education is about questioning, it has to take the next step, that when you question something, you also at least gradually acquire the wisdom of being able to decide if it is worthwhile, it is good enough to be taken forward, and what is not good enough and it should be discarded. And if this quality was not there in human beings, we would be repeating what our ancestors were saying. We would never have, how would civilization have progressed if each generation was not reviewing what was given to it and deciding what to take forward and what to discard and what to add to it.
This isn't particularly a question, but it is in response to your response that indeed a sense of security seems to be lacking in teachers, and that the idea that the point of a teacher is to eventually be redundant. and not to be required throughout. And that idea alone, I have seen tremendously changes the way both the teaching learning process entirely.
Actually, it's not just insecurity, it's lack of faith in the child's ability.
Oh yeah, that too, yes. And it takes security to have faith, doesn't it?
Yeah.
Perhaps. Thank you. Thanks a lot, sir.
Kamal, this is regarding some of the earlier slides regarding scientific temper and the aims that we want to inculcate a scientific temper in everyone. Given that a lot of other forms of knowledge are not amenable to the scientific method, then how does one think of a truly literate person, not just a scientifically literate person, and where does that come into our classroom teaching? So when we study social science, is that something that is taught, or civics?
See, Joy, I think you are basically raising a very fundamental philosophical question. What is knowledge? Knowledge has to be something which has an epistemology, which means criteria of being able to decide that this gets included in this knowledge, that this is sensible and this is nonsense and has to be discarded, right. So, the definition of knowledge goes hand in hand with the epistemology that defines that knowledge. Scientific knowledge has a scientific epistemology to go with it. Okay. Now, of course, there are other knowledge systems that people have belief in, but I think this if this philosophical position is accepted, then each knowledge system also has to define or articulate its epistemology, and then it is for persons who believe in that knowledge to decide whether that epistemology is acceptable to them or not. Yes, of course, there are knowledge systems which don't follow the epistemological rules of scientific knowledge. They are existing, people believe in them, practice them, live by them. But at least I think we all need to make students of science aware that when we talk of knowledge, we also have to talk of epistemology, the rules of that knowledge. Of course, philosophers say, the truth is, what do they say? Belief, what?
True belief.
That phrase is a 3-word phrase which I am sure you can recall that. Plato talks about it, it's a justified true belief.
Okay, so looks like we have run out of questions for the time being, at least. Yes.
So, this is actually related to both today's and yesterday's lecture. So, where we were Sadhna was emphasizing the use of rough work to understand what's happening in the mind of the child. So, in the way you presented the heliocentrism, are there sort of ways in which the teacher or you as someone who's training the teacher ask them to figure out what are those preconceptions or the mental model that the students carry, which you try to challenge? So where does that come into this whole process? So is it a part of a conversation, or is it sort of something they draw, something they
It's all of that put together, but because it is a conversation, so how they join that conversation, the type of positions they take or the type of questions they ask, or you ask those questions and the type of responses you get, that is how a teacher is able to judge what the mental model is. And this is the biggest challenge of the so called constructivist approach or the constructivist model of learning, that as a metaphor what it is saying is that the teacher has a certain structure of knowledge in the mind, and the teacher's task is to construct a similar knowledge structure in the student's mind, right? And all constructivists believe that that construction of knowledge will be done by the student, by the learner, right? And that construction by no means will be exactly in the same way as the teacher desires it to be, or teacher understands that this is the way to construct that knowledge, right? And the teacher really has no way of directly perceiving what is the state of that construction of knowledge in the student's mind. So, the biggest challenge is to keep judging what is getting created in terms of conceptual understanding, theorizing, mental model making, world view that is happening in the student's mind. And then questions like which is the north, and the student saying this suddenly give you a jerk. Arey Baba, what did I do to leave this confusion in students' mind? So, a teacher has to continuously keep devising and asking such questions in order to be able to judge whether the process of construction of knowledge in the learner's mind is going along desirable path or not. Now, in the constructivist debate, the radical constructivists take a position, it does not matter at all. You have to honor whatever construction is taking place in the learner's mind, and as teacher you have no right to challenge it or even examining it. That is the radical constructivist viewpoint, but that helps us to understand the various shades that are there in the constructivism discourse.
So, given every child's natural ability, some may be good at speaking, but some may be better at drawing, or some may be better in expressing themselves differently. So, how I mean, one could call scalable is it to actually interrogate something like this, given that you have a spectrum of children?
That again is a perennial question. The challenge to formulate theories which are very individual centered, and to formulate theories about mass education. So, the school system has to deal with both, because it is a mass education system. We desire to have a mass education system. So, those questions of a large number of students one teacher is handling, how does the learning process take place? Well, when you have the luxury of imagining that one teacher teaching one learner, then you have a different ballpark to formulate your theories. But yes, a very relevant question, but there are many questions which I think to think that there is a process possible by which we will get clear answers to it is not. I mean, there are lots of questions which we know do not have clear answers, and really are very contextual questions. Yeah, I do not have any further clarity on addressing such questions.
It's been a long day like yesterday.
And your train is about to leave.
My train is about to leave, so I better stop. Well, at least I better stop. Thanks, Kamal, for a very engaging discussion. And I hope this is the first of many to come. And we'll certainly have other people coming in here and talking to us about different aspects related to science education in the next, well, if not weeks, but certainly in this year to come. So stay tuned and see you again at some similar occasion. Thank you.
And thank you all for a very patient hearing.